So let's talk now about our last system property, which is invertibility. So we'd like to determine if a system is invertible or not. The system H is invertible if there's a system H inverse, the inverse system, such that for all signals x of t or x of n, where y of t is equal to h of x of t or y of n is equal to h of x of n, we have that we can get back the original x of t by applying H inverse to y. So this system H inverse is called an inverse system. So we've seen this is the same as taking a inverse function of a function. So basically, if the mapping H, our original system, is 1-to-1, that is, it maps different inputs to different outputs, then we should be able to undo the operation of H, at least hypothetically. Whereas if H maps two inputs to the same output, then we wouldn't be able to do that. So to show a system is invertible, you have to show that different input signals produce different output signals, which is saying that the original system is 1-to-1. Or you have to construct an inverse system. So if we look at the system which cubes its input, y of n is equal to x of n cubed, then you can sort of formally argue that if x1 of n is not equal to x2 of n, then there's a time n such that x1 of n cubed is not equal to x2 of n cubed. You just find that time where they differ, and then the cubes will also differ. And alternatively, you can just write down the inverse system. You can say, oh, the cube root system is the inverse system of this cubing system. If you want to show a system is not invertible, you have to find two different inputs, x1 and x2, which lead to the same output y. So if we have the squaring system, y of t computes x of t squared, then if you look at x of t and minus x of t, they both produce the same x of t squared, and because the squaring system destroys sign information. So because of that, this mapping, the original system, is not 1-to-1, and therefore we can't invert it, so there is no inverse system. We should really make a distinction between finding an inverse system and invertibility. Some people call a system invertible only when the inverse system is realizable. So what does that mean? That means that you can actually build it. And so when they mean build a system, they mean build it so that it's online. So they want a causal and stable system that you can plug in, you can build a circuit and stick it in there, and that'll invert the original system. So when they say that a system is invertible, they mean it's invertible with a causal stable inverse. So remember when we talked about causal systems, that non-causal systems are actually very important, especially when you think about doing offline processing of signals. So insisting that the inverse system be causal is really not necessary. But stability might still be important, and if you build a system which is unstable, an inverse system which is unstable, it can be pretty bad, because essentially it means you could potentially create the bad input which causes the system to blow up, and that would be, bad from obviously an operational standpoint, but also, it leads to something like a security flaw. So if you think of something like the power grid, you don't want systems in the power grid to be unstable at all, because they could potentially get that bad input which causes them to overheat and then blow up, and then you get a blackout. So when you're reading about inverse systems, if you're reading in other sources, you have to be a little bit careful about seeing what they mean when they mean inverse system or invertible system. As always, practice is the key to understanding concepts. If you want to learn more about invertibility, you have to try inverting some systems or show that they're not invertible. So here are 4 examples of systems that you can try. I encourage you to take some of the other systems that we talked about in the last few lectures to try and get those and see if those are invertible or not invertible. And I think then you'll start to get a feel for when systems are invertible or not. And of course, when we talk about linear time invariant systems, we'll be able to calculate inverse systems in a sort of more systematic kind of way. So that's it for us talking about systems. And next we're going to turn to focusing on linear time invariant systems.